A galaxy so small you could fit it inside the Milky Way's central bulge is hiding a black hole that shouldn't exist for another billion years. And in the last few days, the James Webb Space Telescope confirmed it. An overgrown, overactive, impossibly young black hole in a galaxy from the dawn of time. This is the discovery astronomers are calling the cosmic fast-forward problem. And the galaxy behind the headline, a tiny red smudge catalogued as CANUCS LRDs 8.6, one of the mysterious little red dots populating Webb's deep field surveys. When Webb first saw it, researchers weren't sure what they were looking at. These little red dots were too bright, too compact, and too red for their apparent age. For months, astronomers thought they were simply young starburst galaxies burning intensely. But then came the new spectroscopic readings, released only days ago, and everything changed. Webb's NIRA-SPEC instrument detected the faint light from CANUCS LRDs 8.6, peeling back the layers of radiation like a forensic scan. Deep in the spectrum, scientists found high ionization signatures, the unmistakable fingerprints of an actively feeding supermassive black hole. This wasn't just starlight. Something extremely powerful was stripping electrons from atoms, flooding the galaxy with high-energy photons. But the shock wasn't that the galaxy had a black hole. It was how big and how active the black hole already is. In the local universe, large galaxies host large black holes. Small galaxies host small ones. It's a growth partnership, a co-evolution. But CANUCS LRDs 8.6 is tiny, yet its black hole is already punching far above its weight class. The galaxy looks like a toddler, but the black hole is acting like a fully grown adult. It's too massive, too bright, too aggressively feeding. Something about its formation skipped the usual rules. The galaxy is seen as it existed 570 million years after the Big Bang. Barely the first chapter of cosmic history. Yet the black hole looks like it has already devoured millions of solar masses of material. For context, that's like finding a skyscraper in a town where people haven't invented bricks yet. This discovery forces astronomers to revisit one of the biggest questions in cosmology. How do supermassive black holes grow so fast? There are two big theories. Massive early stars collapse into black holes around 50,100 solar masses. These tiny seeds then grow explosively, gobbling gas at near maximum speed. But models show this process is very slow and unstable. It shouldn't create monster black holes this early. Giant clouds of primordial gas collapse directly into 10,000 to 100,000 solar mass black holes. These heavy seeds skip the stellar stage entirely. But direct collapse black holes are extremely rare in simulations. CANUCS LRDs 8.6 supports that heavy seed hypothesis. Unless black holes can eat far faster in the early universe than we thought. And that opens a new debate. Did the first galaxies have different physics? Different gas compositions? Denser star clusters? More violent collapses? The spectrum shows that the galaxy isn't forming stars at a high enough rate to explain the radiation. Only an active galactic nucleus, a feeding black hole, can. Its energetic emissions are lighting up the surrounding gas, turning the galaxy into a cosmic lighthouse. And here's the twist. This galaxy isn't alone. Webb has been uncovering more little red dots, each suspiciously bright and compact. If many of them hide similar overgrown black holes, then early black hole growth was not an exception. It was the rule. That would completely rewrite the cosmic timeline. Instead of galaxies forming first and black holes growing inside them, the opposite might be true. Black holes formed first, and galaxies assembled around them. This discovery also hints that early black holes might have played a major role in reionizing the universe, injecting enormous amounts of energy into the foggy cosmic medium during the universe's first billion years. If so, the cosmic dawn was shaped not by young stars alone, but by ravenous black holes. Over the coming months, astronomers will use Webb and ALMA to probe the dust and cold gas around CANUCS LRDs 8.6. If they measure velocities and molecular signatures consistent with an energetic accretion disk, it will confirm the case beyond doubt. But even today, even this week, the message is clear. The early universe was not slow, simple, or calm. It was fast, chaotic, and dominated by black holes that grew far too quickly. And one of them, a greedy black hole inside a galaxy no bigger than a cosmic postcard, is now rewriting everything we thought we knew about how the universe began.